Everybody. So thanks for being here today. Today is an honor for me to introduce you the invited speaker. So it's Dr. Guillem Anglada, who has been so many places around the world. He's an astrophysician. Physicist. I don't know it in English. So he did the degree in physics at the University of Barcelona, and he also did his PhD studies, and then he moved to US, yeah, and to Germany and UK, and he stayed there in the University of Queens Mary, and he got a position there as a lecturer. And now he moved to Barcelona in CSIC, in the Institut of Science, of what? Space Science, yes. And yes, it's an honor for me that he will talk about his most important or relevant or popular discovery about the new planet, the Proxima b. And he will also explain a lot of and plenty of interesting things. So thanks for being here, and the room is yours.
Hello. Hey, can you hear me? Yes, I tend to move a lot, so we'll see how that works. Let's see if I also don't stay over time. Okay, so thanks for the invitation, Laia, and the whole institute. What I'm going to tell you a bit is a bit what we do, not only my work, but kind of this general search for planets beyond the solar system and why these planets are relevant and how this is connected to the search for life beyond the solar system. This is a kind of biology institute in a sense, so hopefully you will appreciate that this is a challenge and that there are a number of things that are interesting. The talk is semi-technical, not very technical, because I heard that there are some physicists here, also biologists, so I'll do my best. Maybe it's a bit, I don't know if the level is right, so we'll see how that works. In any case, what I work, or what many people is working these days, is finding what I call here red terrestrial planets, and you will see in a second why they are red. And the idea is that these are the places where, at least beyond the solar system, are the first places where we can hope to find, or to search, not find, search evidence for life. What means evidence? I'm not saying we search for life, I'm saying search for evidence of life, which is a bit different. Also, because probably you are CSIC and probably you know about this, there is a reto, or desafío of CSIC. Yes, that's called In the Search for Life Beyond Earth, and I'm coordinating this, mostly the exoplanets part, but there's also a search for life in the solar system can be done, also search for life or evidence for life in the interstellar medium. Anyway, I'm more on the exoplanets part. These are just planets orbiting other stars, and you will see in a second. Let's start smoothly. So first, let's get into situation. This is Earth, and you know that, but let's get the order of magnitude of things. The Earth, it's about 6,000 kilometers in radius, but light takes about 1 millisecond to cross Earth. We use light second units as measures of distances. We use something called also parsecs, which is almost the same. But in any case, this is 1 millisecond, just to get the idea. So this is our planet. If we want to go to the next relevant body in astronomy, is the Moon. That would be more or less the real distance between the Moon and Earth, and this is roughly 1 light second. So this means that if you call to the Moon, so you'll get just a 1 second delay, and for example, at some point we want to operate robotically in the Moon, we should be able to do that because it's only 1 second delay. If now we want to go to the solar system becomes much larger. It's kind of a logarithmic scale. So this is a picture of the solar system. The rocky planets are this small circle here. Here you can see the orbit of Jupiter. Here, this is the orbit of Saturn, and this is the orbit of the outermost planet of the solar system, Neptune. Usually people picture the solar system like this, but as you can see, it's not the case. But just to get a sense of a scale, when we move away from the solar system, because I work mostly outside of it, or looking outside of it, if we put the solar system in a pizza, you say, for example, the orbit of Neptune, it's at the border, outer edge of the pizza. In the center, this pepperoni would be the terrestrial planets. If we put this pizza in a landscape like this, where the nearest star would be? what do you think? Is it across the road, which would be pretty far? So the pizza is about 1 light day. The solar system has 1 light day in size. The nearest star to the sun would be here in the entrance of this, my home village, Ullastrell, very, very near here. There is a forest here at about 1 kilometer, where we should put the nearest star if this is the solar system. Any guess? No? Well, yeah, it has to be far, otherwise there's no point. So if this is the solar system, the sun here at the center, the nearest star would be at 3 kilometers. So you see the space, universe, is a very big place. It's pretty much empty. And just to kind of get this distance into your stomach, just transform slowly. This, the solar system here, the sun, and this is Proxima Centauri, Alpha Centauri. And there's nothing in between. So really, around the solar system, up to 1 month's light time, there are some asteroids, something called the Oort cloud, and also the Kuiper belt. These are ancient residual material that from the initial solar system. So these are the nearest stars, and as you can see, it's a very different order of magnitude. It's 3 orders of magnitude difference between working in the solar system, even the farthest planets and the nearest stars. So this is why astronomy and planetary sciences are kind of decoupled. It's very different, the techniques that you have to use here. You can in situ see things, and here you can see that the Hubble resolution, when you look at an object, you don't see anything really, you just see a point of light if you're lucky. So another feature of the solar neighborhood is illustrated in this video that doesn't work, but I'll show you the YouTube version. Sorry, the videos don't work, but I have them here. So this is just a trip going outside the solar system, and what you are going to see is our environment. So you saw the planets going away. Here the Oort cloud. Centauri, dimension, Barnard star, and more. Okay. So one thing that I want you to see from this picture, maybe you know, maybe you don't, maybe you do know, maybe you don't, something that should call your attention is kind of, so anything calls your attention about this picture apart from being pretty? The colors, right? Yes, the colors. So the sun at the center is a yellow star, but most of the dots that we see here, they are not yellow. They are these red dots, okay? I have to go back to the presentation. Yes. So most of the stars, news for you maybe, most of the stars are not like the sun. The sun, you have been told that is a regular star. It's not. The sun is a massive star. The sun is on the top 20% of massive stars. Most of the stars are what we call red dwarfs. So the sun would be a yellow one here. And there are these orange dwarfs, a little bit smaller, and then smaller, like 60%, less than 60% the mass of the sun. They are not much smaller, up down to 10% the mass of the sun. These are called red dwarfs. And in numbers, they are the most common. They are not the ones that are bright. They are not the ones that accumulate most of the mass. Most of the mass in the galaxy and in the universe is in the very massive stars. But in numbers, these are the most common stellar types. So I will give you 3 take-home messages today, and this is the first one. When we look for planets or places in the universe, most of the places, or these small pizzas around where you can find things, these are mostly around red dwarf stars. And this is one of the reasons why we study red dwarfs and try to find planets around them. There are 3 of them, you will see. So that's the sun. So take-home message, most stars are actually red dwarfs. Another ephemeris, if you want, or just a fact, is that you don't see any of the red dwarfs when you look at the night sky. All the stars that you see, the lowest mass stars that you see are some of these orange dwarfs, and the nearest ones, for example, G dwarfs. The ones that you see actually are very bright, massive stars, 10 solar masses that are very far away, or another popular star is called Betelgeuse. It's been in the news for a while because it's doing strange things. It may explode as a supernova. It's relatively nearby, so hopefully we don't get burned. But that star is red, but this is a supergiant star. It's about 600 light years away. The nearest star, it's 4 light years away. Okay, so most stars are red dwarfs. And now the question is how we find planets around other stars. As I mentioned earlier, it's very hard to see anything around a star. The stars are luminous, so at least we see a point of light, but the planets are not luminous by themselves. They are a bit luminous in the infrared because they are at 300 kelvins, 200 kelvins, things like this, where you have thermal emission. But in general, they are many orders of magnitude fainter than the stars. So typical ratios of a planet with a star is 10 to the 6, 10 to the 9. So 1 million or 1 billion times fainter. So when you look at the star, you want to see a planet orbiting it, that it's 10 to the 6 times fainter. You have this halo of light around the star that makes very difficult to see anything really there. There are techniques that we are developing. We would like to make direct images of planets. We want to see this spot of light and then make spectroscopic measurements on these planets to learn things about them, but this is very hard at this point. However, we are detecting planets still, but what we use is these 2 methods. One is called the radial velocity and the transit method, which are called indirect methods. We don't see the planets themselves. What we see is what the planet does on the starlight. The first one that I'll introduce quickly is what's called the transit method. It's kind of the simplest one. You don't even need to have a PhD to understand it. It's basically you have a star, and if the planet goes in front of the star, it blocks part of the light. You don't see the structure, you don't see the disk of the star, but you see the light of the star kind of dims, and it does it periodically. So from that, you get the orbital period. From the size of the dimming, you get the size of the planet. Of course, that requires the planetary system that we are looking to has to be aligned to our line of sight, which means that this technique is good to find planets, but only a small percentage of planets can be found. So if you look at the neighborhood, 200 stars in our neighborhood, this diagram that I showed you, you would find 3 or 4 planets around this that are transiting. So this technique is very good. It's telling a lot because we are looking at millions of them, but very far away. So this technique has allowed us to make statistics and understand what kind of planetary systems there are around. Let's see. Well, let's just keep this. So this is a plot showing kind of the discoveries of one very successful mission. It's called the Kepler space mission from NASA. It went to space to try to detect planets using this technique. From space, it's easier to detect planets because what you want to see is the light of the star very constantly. The atmosphere of the Earth is very disturbing to photometric measurements. But if you go to space, this is very stable, and then you can reach the sensitivity sufficient to detect Earth-sized planets around sun-like stars. And this is a bit of the summary of discoveries of Kepler. This is just raw discovery. So you discover a planet around a star, you put it in this diagram. So one thing that might call your attention is that, for example, Mercury would be somewhere here. And if you look at the bulk of discoveries of Kepler, you see that most of the stars actually have many, many planets in close-in orbits. Typically, the most typical planetary system is not like our own. Most planetary systems contain 2, 3, 4 Earth-sized planets or a bit larger in very close-in orbits, orbital periods of 10 days. If you put a planet like that around a sun-like star, that planet would be very hot. However, as I said before, most of the stars are these red dwarfs, and these red dwarfs are fainter. This implies that the amount of energy coming out is lower. So actually, the fact that we have so many planets in close-in orbits allows us to detect this. This is a coincidence. We didn't know that 10 years ago. We just discovered it with the Kepler space mission, that actually all these stars have these planets, and then there are these red dwarfs, which are fainter, and therefore the place where the planets are more common is where the red dwarfs have these planets, and they are temperate in the sense that the temperature, equilibrium temperature at the surface of this planet is similar to our own. So that led to the take-home message number 2, is that most stars, it's not only for red dwarfs, it's also for sun-like stars, even more massive, have all these very short period planets and very small planets, which is good news, and this is relatively recent knowledge. So the other method that we have to detect planets is called the Doppler spectroscopy, and this works like a speed radar in a highway. Basically, we look at the star, and we look at the light we see many spectral lines of this light. We separate it with a spectrograph to get high resolution. We see individual molecules, individual atomic lines, and then we measure some of them, and by measuring the Doppler shift, because light is a wave and it behaves like sound, so when the star comes to us, the light gets blue shifted. When the star moves away, the light gets red shifted, it loses energy. So monitoring this, as if the planet orbits the star, then the star also orbits the common center of mass of the system, and measuring this very precisely, we can infer the presence of planets. Just to show you how challenging this is a spectrum of, for example, a sun-like star with a spectral line, an atomic line, and this is the width of the line. And if, for example, the sun was a spectroscopic binary, two stars orbiting one around each other, you would see that the line moves a lot, even by eye. You would see it in the spectra that the line is moving over the years, for example. But if you have a planet, even a planet like Jupiter, the shift in the line is very little. And just to show you the second, to detect Earth-sized planets around sun-like stars or others, we need to reach the precision of 1 meter per second. So this is a signal of 300 meters per second, and you already don't see anything, right? So if we look at the bottom of this spectral line here, this is what I'm showing here. I'm going to show you what's a 1 meter per second shift, or 3 meters per second. So this is, you see? Well, it's moving, so you see it by eye. Yeah. The problem is that usually even very high quality data is something like this, right? So and then you need many of these spectral lines, you measure them simultaneously, hundreds of them, and by doing statistics, this is a spectrum of the sun with the many spectral lines that it has. You just centroid, or there are some more sophisticated data analysis techniques, but essentially use the collective information in the whole spectrum to get to precisions to meter per second level. And with this is how you detect a planet with this technique. You go there, you look at the star, measure the velocity as in the radial direction, and you go one day and you get some measurements. So it's moving away from us at 100 meters per second. Now it keeps moving away, but it's changing the velocity of the star. Otherwise it would be flat, so there's an acceleration, and keeps moving, and at some point, if this is a planet orbiting the star, you see this folding, and from this you infer what's kind of the mass, also the orbital period of the planet by just looking how often this repeats. This is a very easy planet to detect. This is a 5 Jupiter mass planet around a sun-like star. Typically, Jupiter is 300 times more massive than Earth, so the signal for Earth-like planets will be 100 times smaller. So here you don't see the noise. But when we look at really challenging objects, I'll show you later, it's much more complicated. It takes a long time with this method. If you want to look for planets that are orbiting at periods of 3-4 years, you have to wait 3-4 years at least to see one cycle. And if you want to be sure that it repeats, then you will have to wait 9-10 years. So a lot of patience, good. That was an easy one. Here is just an illustration of how this method has evolved over time, and I also want to show this because these are Michel Mayor and Didier Queloz, and they got the Nobel Prize for discovering the first exoplanet around a sun-like star in 1995, and this year they got the Nobel Prize. And you see, this is the mass of planets, so Jupiter would have a mass somewhere here, and this is in logarithmic scale. That would be 1 Earth mass planet. And as you see, over time, technology, methods have improved. The baselines also improved, so we can prove longer and longer orbital periods. And the detections of planets started to increase a lot. And we are somewhere here where we can reach now instrumental precisions at the level of meter per second. And we are detecting some Earth mass planets. They are not easy to detect, not only because of technical reasons, also because of astrophysics. The stars are not perfect balls. They have spots, they have pulsations, they have magnetic fields. What you measure is the integrated light coming from the whole star. So if you have different contrast in different parts, the star is rotating, and then it looks like the star is moving, but it's really not. It's just the effect that the spot would have on the spectral line. It distorts the spectral line, and when you centroid the lines, you get artificial effects. So that's kind of the noise floor at this point, not instrumental. It's coming from the stars themselves. We reach this point at 1 meter per second where it's hard to get higher and higher precision. This is a bit of a problem because the signal of Earth around the sun is 10 centimeters per second. So with this technique, we are limited by the stars to be able to reach Earth-sized planets. The transit one works better, but again, the transit one, you really need to look for very far away planets. So this is a bit of a problem, except that then we have the red dwarfs coming to save us again, because the red dwarfs are smaller. which means essentially they are sun-like stars. The only thing is that they started with much less mass. So typical red dwarf is 10% the mass of the sun. So this means that the signal will be larger. Also, because it's fainter, the orbits at which a planet can remain temperate, for example, that would be a sun-like star, the orbits are closer, and this provides the third take-home message, is that planets around red dwarfs, planets in temperate orbits around red dwarfs, are also easier to detect. The combination of these three effects is what makes, now these days you will see sometimes in the news, oh, new Earth-sized planet around a star. All these planets are all around red dwarfs. For sun-like stars, we are probably a decade still to detect things like this. Also in numbers, the nearest ones are around red dwarfs, so it can make sense, and these are the planets that we will be able to learn more. So my business here is try to find the nearest of these Earth-like planets, Earth-sized terrestrial, let's call it this way, because in the near future we will have instrumentation that will allow us to get spectra of these small red dots. That's just a summary of what I just said. And this is a picture, general picture for if you are interested on exoplanets, the kind of planets that are in the universe. This is a very important plot and has a lot of information that I don't have time to summarize or describe. But essentially, there are like 4 kinds of planets. There are gas giants. This is mass. So this would be planets like Jupiter or Saturn. This is the orbital period. Then there is a class of planets called hot Jupiters, which are like Jupiter, but in very short period orbits. For some reason, there are no planets like Jupiter in intermediate orbits. There are reasons, the models are telling us a lot of this, but there are a lot of challenges. A lot of the structure here comes from physics. And here, down, we have things that we call Neptune-like planets, like Uranus and Neptune in mass, but most of them are warm. We find that they are very common as well around sun-like stars. We don't have any in our solar system, but in most planetary systems, they are there. And something called super-Earths, which we essentially have no clue what they are, because we don't have any analog in the solar system. So the Earth is 1 Earth mass, the next planet is Neptune. In between, from Neptune is 20, so an object of 10 Earth masses. Although they are very popular and common, we don't know what really they are. I mean, we have an idea, we think that they are intermediate cases. It's a question if there is a transition, a smooth transition from rocky planets to Neptunes, and there's a lot of theory behind this. Okay, anyway, this is just a picture in case you are interested in a bit more the bigger picture. And also you see there's a paucity of planets here. This has to do with the planet formation process. When a planet gets enough mass, essentially when it's forming, usually the star is young, there's a lot of gas, and they very quickly accumulate mass and go to become a classic giant. So again, there's a lot of information here. Also, this structure has a reason. Anyway, later we can follow on this in any interested. Let's go back to Earth, and what I said before, this is what I do, try to find the nearest exoplanets to the Earth, and if this is Earth, we'll just put it here. This is the pale blue dot image taken 25 years ago. This was the 25th anniversary of this image. This was taken beyond the orbit of Saturn. Looking back, Carl Sagan contacted NASA, and after insisting a lot, he managed to get, I think it's Pioneer or the Voyager, Pioneer probe to point back and take a picture of Earth at the Saturn's distance, and this is what you see. This is called the pale blue dot picture, and this is just a stray light from Saturn and things like this. Anyway, if this is us, this is where we are, the sun, and these are kind of the nearest stars. So these are all the stars that are within, let's say, 4 parsecs. These are about 10 light years. So as you see, many of them, most of them are red dwarfs, and we are trying to find as many of these nearby planets as possible. Of course, there are more red dwarfs, so we are finding most of them around red dwarfs. So the first one that we looked in detail, people has been looking at it for a long time, and part of our work actually was to collect this historical data and find evidence if there was maybe a planet orbiting this star, is Proxima Centauri. Proxima Centauri is part of the triple system Alpha Centauri. Because the orbit is very long, at this point of time, Proxima Centauri is closer to us, and this is why it's called Proxima. It's a red, irrelevant star in the cosmos, but it has a feature that we found out 3 years ago, which is that it has a planet at least, probably 2 or 3. Here there's a video that I'll show you what we did, the experiment that Laia was telling, the discovery of this very nearby terrestrial planet. At this point of time that we have discovered so many planets doesn't look very relevant, but has been the holy grail for many years to try to find the nearest exoplanets that may be similar to our own. And this is the campaign that led to that. Let me show it. Instead of talking, I can show a video which is more eloquent, not the whole thing.
Go behind the scenes and find alien worlds beyond our solar system is one of the most exciting and... The quest to find alien worlds beyond our solar system is one of the most exciting and captivating fields of modern astronomy. And a unique new project will now allow members of the public to go behind the scenes and follow a planet hunt as it happens. This is the ESOcast.
The ESO is the European
Cutting-edge
Southern Observatory.
science and life behind the scenes at ESO, the European Southern Observatory. .2 light-years away, in the constellation of Centaurus, lies Proxima Centauri. This small, faint star is one of about 160 billion red dwarfs in the Milky Way. But this red dwarf is special. It's the closest known star to the Sun. As our closest stellar neighbor, Proxima Centauri has been extensively studied by space and ground-based observatories. Tantalizing but inconclusive, hints that an alien world may orbit the star have been found. Now, a new and exciting scientific and outreach project known as the Pale Red Dot Campaign will conduct a more sensitive search than ever before for an orbiting Earth-like planet. The campaign's key observations will be carried out by ESO's High-Accuracy Radial Velocity Planet Searcher, or HARPS, which is attached to ESO's 3.6-meter telescope at the La Silla Observatory. This extremely precise spectrograph will monitor Proxima Centauri's motion, looking for the minute effects of the gravitational pull of an exoplanet, which causes the parent star to wobble back and forth. This tiny motion can be detected by HARPS through tracking its radial velocity over time. But stellar activity could mimic the presence of a planet. To address this, HARPS measurements will be complemented by data from other telescopes around the world, including the Las Cumbres Observatory Global Telescope Network and Boötis, the Burst Optical Observer and Transient Exploring System. The observations will be conducted between January and April 2016. Blog posts and social media updates throughout this period will reveal the latest progress with the observations and provide a rare opportunity to see how science is done in modern observatories. But don't expect astronomers to tell you right away if Proxima Centauri has an exoplanet. The answer will likely come after some more months of work and once the result is reviewed by other astronomers. That's how science works. To follow the live observing campaign, visit the Pale Red Dot website, Twitter account, and follow the hashtag PaleRedDot. No one can yet know what the observations will discover, but the journey can often be as exciting as the destination. So join us as we attempt to take another historic step towards answering the biggest question of all. Are we alone?
Okay. Let's see, can get the presentation back. Yes. So, that was the Pale Red Dot campaign. We did something a bit strange here. We thought that there was a signal, But we got the time to do observations. This is how we astronomers work. You have to apply for time, and then you get some telescope time for a number of months, like in this situation. And we were pretty sure that the detection would be confirmed, but we weren't really sure, right? We had the statistical evidence, so we announced that we are going to do this experiment. This was not seen ever in the exoplanets field. There's so much competition that you never tell what you are going to do, right? But we just did, okay, we are the only ones that we can have this experiment done, and we were sure that the experiment could lead to a breakthrough. So we announced it and made an outreach campaign with blog posts, comments, also showing some data during the observations, and then coordinating also with observatories all over the world to get this done. This is just a sample of people that participated, and then the European Southern Observatory are kind of the official European observatories, although they are in the south in Chile. They are the biggest ones in the world. Kind of helped us in the outreach campaign and also in the science. We got a lot of support. As you have seen, this video was done before the planet was, the scientific campaign was done. So there was some of our colleagues who say, well, this is very risky what you are doing, because then if you don't find anything, people will get depressed, and that's not, well, we got lucky. And also it helped a lot also to spread the result later, because there were a lot of science writers and journalists that were following as well, apart from general public. Anyway, the campaign was successful. We collected 60 measurements on Proxima Centauri, and this is what you see here. Just for you to compare, this is the signal that you see from a Jupiter-like planet around a Sun-like star, and this is what we see, this ratty sinusoid spanning over 2 months. So it repeats every 11 days, which means it is orbital period, and from this you can use Kepler's third law, and with the amplitude, how much the star is moving, it's about 1.4 meters per second, so it's moving at walking speed, essentially. You can derive the properties of this planet. It has a minimum mass of 1.3 Earth masses, good. Also, it's at orbital distance, 5% of an astronomical unit. This is the distance of the Sun and the Earth. This means that it's very close to the Sun, and also has an equilibrium temperature comparable to our own. So that was a big thing and led to a lot of important things. That was the first physical press release that ISO did ever. NASA does press releases all the time, but ISO, they were very afraid, doing a press release is not a very European thing to do. But we thought that this was important, and actually after this, there have been several. Some gravitational wave detection has been here, and things like this. So just for you to compare, this is Proxima Centauri. That's what we call the habitable zone. It's just a name that some people debate if we should call it habitable zone. It just means that the orbit where the planet should be warm, not cold, not hot, so it can have liquid water on its surface, and this is just to compare to Mercury's orbit. So you will see these planetary systems are really compact, very different from our own. Okay, so because it worked, we continued. We created follow-up campaign called Red Dots. Now it's not only using professional telescopes. We invited actually semi-professional astronomers all over the world to help us with this follow-up, because what we need, apart from measuring the velocity, we need almost continuous monitoring of the star to get all the spot activity and things that perturb the measurements monitored. And that worked relatively well. For example, the next star, Barnard star, is this one here, the next red dwarf. These two are too difficult. We are not doing them for now. But it also led to a planet discovery. Barnard star, does it work? Oh no, there was a video, of course, doesn't work. So no video, anyway. This planet is different from the Proxima b or even our own. This is a 3 Earth mass planet in an orbit of 230 days, although the orbit is similar to our own. This is a very cold planet. It's about 100 Kelvin. Again, it's a red dwarf, and at the distance that it is from the star, the planet is really cold. Anyway, it's very nearby, again, a nearby star, and this is just to compare again this beautiful curve of a Jupiter-like planet, and this is how the signal of this planet looks like. We had to combine data from 8 instruments taken over 20 years to kind of provide more or less convincing evidence, although this is not as robust detection as Proxima b, for example. Okay, so we keep going, and this program has been very successful, so successful that it's kind of easy now to find these planets. This is just showing you Proxima. We did not Alpha Centauri, but we did Barnard star, and then we kept searching. So planets around Epsilon Eridani, that's another star. This one, it's almost accepted publication. And some of these stars, you don't see it, but they are circles. This means that we have found planets. And this is just to show you how many of these we have found with this strategy. There's a lot. This is a very beautiful one. It's a 3 Earth. There are 3 planets like Earth, and 2 of them are in the habitable zone, for example, and this as well. It's a nice one. And there are some other groups as well that are looking at this. We are not the only ones. People realize that these are easy to do, so everybody jumped on it. Okay, good. So, okay, we are finding the planet, but we want to learn a bit more. Otherwise, it's just a signal, a sinusoid that gives us some knowledge. Now we know the population of the planets. The space missions have given us the bigger picture. We are detecting the nearest ones. Why are we finding the nearest ones? Because we need photons from the star. We need a lot of signal to be able to characterize these planets eventually. So what we want to see from the planet, we want to see reflected light coming from the star that goes through the atmosphere and reflects back on the surface. Therefore, this light has the imprint, the spectroscopic signature of the atmosphere. We also want to see these planets in emission. These planets emit light in the infrared, especially, for example, Earth. Its peak emission is at 10 microns. It's near infrared. And in transmission, sometimes when these planets transit, the light of the star goes through the atmosphere, although most of the light is blocked by the planet itself. Some of it just goes through the atmosphere, and again, it imprints some of the spectral information of the atmosphere. So how we learn more? So when we are lucky and we have these transiting planets, the nearest transiting planet that it's good or Earth-like is a system called TRAPPIST-1. It's also very famous for the people that follow it because it has 7 Earth-sized planets, 3 of them also in temperate orbits, but it's farther away. It's about 30 light years. So the signal is much, if we had the same system around Proxima Centauri, in 2 or 3 years we should be able to detect all sorts of molecules, but this star is far away, and we will not get that lucky to find transiting planets close to the sun. What we do in the transit method, we try to see light in transmission and in emission. Basically, when the planet goes in front of the star, you measure the planet in many different wavelengths, and if there is a, for example, water molecule absorbs at 1.5 microns, it looks like the planet is larger at that wavelength, because it has a larger cross-section, it blocks more of the light of the star, and from this you build up a transmission spectrum. This is just an example. And in emission, what you do, you wait until the planet goes behind the star, and then you compare the transit before, well, you compare the light of the star before and after the transit, and you see a small difference, again, as a function of wavelength that tells you, again, spectral information on the atmosphere. So this is an example. So this is basically measuring the size of the planet as a function of wavelength, gives you spectroscopic information. And if you have carbon dioxide, it has very, very well-defined absorption bands. Methane, water, also produces absorption bands, carbon dioxide, carbon monoxide, and methane. This has been done on a hot Jupiter. This is a planet like Jupiter, very, very big, but very close to the star. These planets are very easy to detect. This is why we found, but there are not that many. In any case, these planets are being now surveyed with Hubble Space Telescope, and we should be able to do the same with terrestrial planets when we have James Webb Space Telescope, which should have been launched already, but the thing gets delayed, so maybe in a couple of years we are lucky and it goes through. And then ESA has also a small probe, an M-class mission called Ariel that will do the same, but 2028, a bit later. Anyway, we would like, this is one kind of planet that we want, the ones that transit, but very few of them are nearby enough of the solar system. So what we want to do is get pictures of planets. And for this, there is a technique that's called adaptive optics, because we want large telescopes, and large telescopes in space is too difficult. We can put things large, but not large meaning 40-meter telescopes. So the largest one that we are going to launch, James Webb, will be 6 meters. But we need 40-meter telescopes to really get enough photons. So for this, we need to get images, and this is an example of a technique. It's called adaptive optics. What we do is correct for all the distortions of the atmosphere in real time, so you get a sharper image. And instead of seeing this, what you see is all these dots. This is an image of a galaxy cluster. Okay, so this is how it works. And with this actually works. It has been demonstrated, works better in the near infrared. This is a planetary system around nearby, not very nearby, but this is a very young star. So the planets are young, and when the planets are young, are self-luminous. When the planets condense, the energy of the gravitational energy gets radiated in terms of thermal energy. And this star has 3 Jovian, very massive planets in very long period orbits. But we have so good data. Let's see if this video works, because it's a GIF. Yes. So this star has been observed over an interval of 10 years. And you see the planets in motion. So this is just Keplerian motion of these planets. Might seem trivial or a cartoon. There's a lot of work to have something like this. Is kind of amazing. And you can see that they follow Kepler's law, and this is a very good, very well-studied system. Anyway, so how do you learn more? This is very good. We can get all the light of the star in the center, so we can try to find out faint things, but this is not enough to detect terrestrial planets. The contrast ratio here is about 10 to the 3. These are gas giants that are luminous. I said before we need to reach contrast ratios of 10 to the 6, 10 to the 9. So to do this, there are a number of techniques that we are combining. We have adaptive optics to get all the light of the star in the center. Then we block it with a coronagraph and do some manipulation of the phase to make interference. And at the end, we put spectrometers in each pixel. Instead of putting a detector, what you put is a spectrometer, like hyperspectral imaging. And from this, the spectrum of the planet is a bit different from the star, and you can play tricks to be able to enhance the contrast farther out by a factor of 1,000, 10 to the 4. So the combination of 10 to the 3, 10 to the 4 from adaptive optics with the spectral enhancing allows us, in principle, to reach 10 to the 8, 10 to the 9, which is what we want to do. And this is just an example of some technology that we've been developing, trying to do spectrometer units because we need hundreds of them. And nowadays, these spectrometers, each one costs $1 million. So we need to make them cheap. And this is an example of something that we did that cost about 10,000. And then we have to replicate this many times. Anyway, exoplanet is very popular. Lots of things are happening. This is just an illustration. This means also that there are a lot of missions that we will do exoplanets. This is the flagship next NASA telescope, James Webb Space Telescope, that will replace Hubble. And then ESA has a planet detection mission, not characterization, first in 2025 and 2030, there's Ariel. But of course, what we want is large telescopes, like the European Extremely Large Telescope, which is being built already. And it will be a 40-meter telescope, and that coupled with spectrometers in principle, within a decade, we should be able to get images of planets. So don't get your expectations high. This is just an exercise to see that you are not sleeping. Let's see, if we want to image a planet around Proxima Centauri, for example, what we would see these days is a pixel, basically. The PSF, the planet, you cannot resolve anything with a small telescope. How large a telescope would need to be to get an image of 3 times 3 pixels? Anybody can guess? So this would be like, say, 5-meter telescope, give you a pixel. So how large should the telescope be to get 3 by 3? How many? 10 times, you say that's 50 meters. Yeah. 50 meters. So we'll see. Anybody else? Anybody else wants to guess? 3 times, 15 meters? No, it has to be 46 kilometers. So forget about it. I mean, you can also use interferometry, which allows you to do tricks with light and things like this, but it's not feasible to actually get detailed images. If you want an image like this, like Earth, from Earth on a nearby star, you would need a telescope the size of the Earth itself. So that's not going to happen. Well, in space, again, you can do tricks, which is putting many telescopes very separated and try to do interferometry. But at this point, it's science fiction because we don't have the infrastructure in space to do these kind of things, and it won't happen until probably the next 100 years. So don't get expectations high. Yeah, we are going to find evidence for life, but not life. Things like the canals of Mars. Forget about it. This was somebody thought Lowell. From Lowell Observatory, the astronomer that also found Pluto, looked at Mars and saw a lot of canals, thought it was evidence of life and a civilization, but it was not the case. But we cannot even make these guesses because we won't have the level of detail. And even so, there was, for example, in Martian asteroids, or if you go to Mars, you can look at microscopically if you see evidence of microbes or things like this. We won't be able to do that. At most, we'll be able to have things like this sinusoid, or get a spectra and see spectral features of chemical species that, if they were left in the atmosphere of that planet, would disappear, for example, what I mean. If you have oxygen alone, that's not what's called a biomarker, because oxygen can be formed by abiotic processes. It can be delivered from comets, and also when you have dissociation of of water, the hydrogen leaves, and if the planet is a water wall, which we think most of these planets are water walls, what we'll have, the hydrogen works, flies away, and then the oxygen oxidizes the planet and everything it can, but at some point it gets saturated and builds up an oxygen atmosphere. But if in that atmosphere you also find traces of methane, methane and oxygen react very quickly, and in a few years they would disappear. So what you want to see is combinations of gases that in principle should not be long-term stable from natural processes, let's say. With this sentence I made a lot of statements, and there's a lot of people working on this, on all the possible false positives, all the combinations. Now, for example, in Mars, there's evidence of methane. Because it's not clear what's going on, but it looks that it's intermittent, it's not clear if it's coming from the underground, it's an instrumental effect, or things like this. So this is the same we want to do, but on remote exoplanets when we get a spectra like this. And that should be it. If we get lucky, we will get a pale red dot picture maybe in 10 years. We can repeat this talk then, and we can see where we are. Anyway, the next thing that you want to do maybe is send interstellar probes, but again, this is even longer shot. There was a beautiful video that would illustrate how even if you send an interstellar probe at 20% the speed of light, you have like 3 seconds then to take a picture. And you are at 4 light years, so transmitting back would be a problem. So it's probably not going to happen. That was the video. It's not there. But with this, I think I finish, because this was the picture of the pale blue dot, and what we are seeking now is the pale red dot picture that hopefully within the next decade we should reach it. Thank you very much.